So let us first look at, maybe I should use a different color. Let us say functions from x to 2 and power set of x for a set x. These two are in bijection. Yes, so given any function f from x to 2, what will you map it to under power set? So 2, remember 2 is 0, 1. What can you map it to?
If the image of x is 1, then map it to the set containing x.
Exactly. So f inverse of 1. F inverse of 1, which means all those elements x in x such that f of x is equal to 1. Yeah, all of you know the definition of inverse image. Right, so this f mapping to f inverse of 1 is the mapping in this direction, and conversely, given a subset y, you map it to the characteristic function of y from x to 2. Characteristic function, I am writing the letter chi. This is fancy x, Greek x. Yeah? So this chi, it takes an element x to either 1 or 0 depending on what it is, if x belongs to y and 0 otherwise. So this is the characteristic function. Of y. So you can easily verify that these two functions are inverses of each other. Yeah, start with a function, then you map it to its inverse image of like f inverse of 1, and for f inverse of 1, well, the corresponding characteristic function will be precisely f, and conversely, and the other direction also. Understood this? Yeah, I am sure you have seen characteristic functions. Yes? You don't know what is f inverse 1? I am saying, so chi sub f inverse 1 will be a function from x to 2. This will be actually f. And also for every y, yeah, so y is also equal to chi sub y inverse of 1. Yeah, please check these two identities yourself, convince yourself that this is indeed the case. Okay? So let's go ahead. There was one more argument that was coming up yesterday in the class. So let us do that. So p fin of x. Can you understand what this is? What is p of n? Power set. So p fin of n? Set of finite subsets. Yeah, okay. So x subset of x is finite. Okay. So we want to show that p fin of n is actually countable, countably infinite. Yeah. How do we show that? Yeah. Loudly. Bijection with?
Natural number.
Bijection with natural numbers. Yes, I am asking you how. Yeah, that's our goal, to find a bijection with natural numbers. What is the meaning of a finite set? That there is a bijection of that subset with with some natural number. Well, one simple way is to fix that natural number. So I am going to write down, yeah, clearly P fin of n is the disjoint union of n to the power k, where k belongs to omega or natural numbers. Yeah, this is disjoint union. All of you agree with that? Because every subset is in bijection with exactly one natural number, not two different natural numbers. So therefore, this is actually a disjoint union. It's equality. Sorry, I should not say equality, I should say they are same. Okay, now is n to the power k countably infinite? Yes. Why? N to the power k, n cross n cross n, k times.
Because n cross n cross n is countably.
N cross n cross, yes. So n is countably infinite. So finite product of countably infinite sets is again countably infinite. Therefore, each n to the power k is countably infinite. Yeah, each n to the power k is countably infinite. What is the argument? That because finite product of countably infinite is again so. Now finally, arbitrary union, like countable union of countably infinite sets. Is that countably infinite?
Under with choice.
Modulo, yes. So modulo or assuming, yeah, maybe that's the better word. So assuming AC omega, the countable axiom of choice, disjoint union of n to the k is also countably infinite, and hence so is P fin of n. Actually, these two sets are not exactly the same, right? Every finite subset, let's say 2-element subset of natural numbers. Yeah, I am talking about this one. 2-element subset of natural numbers. What happens with that? Let's say 1, 2. 1, 2 and 2, 1. Yeah, they are distinct elements over here in n square. So we are counting something larger. So I mean, perhaps ideally I should write down this particular thing as a subset. But I know by singletons that natural numbers are contained inside finitary power set. So therefore, by Cantor-Schroeder-Bernstein, everything will work. Yeah, because we have shown that this side is countably infinite, and this is at least countably infinite, therefore it has to be countably infinite. CSB theorem. However, we have one more very genius way. Somebody already said these arguments yesterday in the class, but I wanted to do it separately. One more way to deal with increasing the set of increasing sequences is this set of finite strictly increasing sequences of natural numbers. Okay, what do I mean? I'm choosing something. Yeah, A0 less than A1 less than A2 dot 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 AN. Now this is a sequence. This is a finite sequence. It is strictly increasing. Yeah, and all of them are natural numbers. So any idea how to count elements of this particular set? These are all ordered. Somebody told me something about primes yesterday. Okay, what are primes? So list primes in increasing order. Say P0, P1, P2 and so on. How many prime numbers are there? Infinitely many. Who proved this? Euclid, yes. So Euclid's proof of infinitude of primes. Okay, good. So P0, P1, P2. Yeah, what is P0? 2. P2 is 3 and you know the prime numbers, right. So now, if a particular element is in the sequence, it's a finite sequence. If a particular element is in the sequence, then we include it in the product. So map this to P sub A0 to A0. Okay, I can also do that. P0 to A0 is also fine. Or even if I just take different powers, yeah, P0 to so P0 to A0, P1 to A1 and dot 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 Pn to An. Map this sequence to this particular product. This map is injective because of fundamental theorem of arithmetic. Yeah, the map is injective thanks to fundamental theorem of arithmetic. Okay, so that means from the sequence, from the set of finite sequences of natural numbers to natural numbers, there is an injective map. Obviously, from natural numbers to the set of finite sequences, there is an injective map, namely singleton sequence. So everything works nicely. By using CSB theorem, again this thing is also finite. Countably infinite. This set is also countably infinite. Now I want to point out something from the last slide, and which is this part. So to prove the same result, we use two different techniques. This is precisely, yeah, P fin n is the collection of finite sequences. We can always arrange them in increasing order. So therefore, we have used two different techniques to prove the same result. One technique used axiom of choice, countable choice. The other technique did not use axiom of countable choice. So this says something, that axiom of choice is not always necessary. If you know something about the sets involved, then you don't need axiom of choice. Yeah, for natural numbers, we know a lot about them. Yeah, we understand every single element, we understand relationships between different elements. So we don't need axiom of choice to deal with natural numbers. If there are sets, infinite families of sets, about which we have no idea, they are arbitrary sets. then you will need axiom of choice to define a choice function. But right now we don't need axiom of choice because we already know natural numbers properly. Okay, this is just a feature of axiom of choice. Okay, so I have very little time left today. So our goal for next class will be this. So all of you agree that 0, 1, this is an interval in R, so therefore it includes, I can use the inclusion sign, it includes inside real numbers. Yes? Okay. Then we are going to include real numbers inside the power set of rational numbers using Dedekind cuts. Okay, we'll do this on Monday. Then power set of rationals is what? Well, it is precisely, it is in bijection with the power, with the set of functions from Q to 2. All of you understand this? Yeah, we have done this today. Then this, there was an exercise yesterday which we did in the beginning. This is in bijection with functions from natural numbers to 2 also, because natural numbers are countable, so naturals and rational numbers, there is a bijection between them, right? So then there is something like P of n, power set of natural numbers. Oh, sorry, I don't even need this. Maybe I am writing this unnecessarily. So finally, from here to here, we will define embedding using Cantor's middle third set. So now look at this particular circle. Everything is an inclusion or embedding or bijection. Therefore, by CSB theorem, all of them have the same size. All of them have the same cardinality. They are equinumerous. Right? So these are the two topics for next lecture, Dedekind cuts and Cantor's middle third set.